Let us define what we mean by scalar field. Consider a region of space and at each and every point in this space we can measure temperature. Suppose this is the origin and a typical point or a representative point is P. The coordinates are x, y, z, and this is vector r. So for all such points in this region there is a temperature. In other words, temperature is therefore a function of vector r or x, y, and z. We will say that in this region there is a temperature field, and since temperature is a scalar quantity, it is a scalar field. So the formal definition is in a region of space, if to each point P a scalar, say psi, which is a function of position, is defined, we say that a scalar field psi exists. In that region. So example of a scalar field is temperature field. Let us give another example. Suppose this is the origin and a charge is placed here. The charge produces its effect in the surrounding region, and suppose this is the region of interest to us. Now in this region of interest, this charge will produce its potential, and suppose this is a typical point P having coordinates x, y, z. This is vector r, which is the position vector of the field point P with respect to origin O. The electrostatic potential here is given by Coulomb's law. Clearly, at each and every point in this region, we have a V. So we will say that in this region, a scalar field exists, and the scalar field is the electrostatic potential. So in this region, the scalar field is the electrostatic potential V due to the charge Q. So temperature field, electrostatic potential V, these are all examples of scalar field which are defined in a particular region of space. We now discuss vector field. Suppose this is the origin, and here we place a mass which has a charge Q, and the region of our interest is this region. So this is the field, and in this region this particle will have its influence. It will produce a gravitational field which is given by Newton's law of gravitation. So let us consider any point, typical point P here. These are the coordinates. This is the position vector. This particle, which has charge Q, will produce an electrostatic field here, which is given by ES for electrostatic. At each and every point in this region, we have a value of gravitational field as well as electrostatic field due to this particle. Therefore, this is said to be a vector field. The vectors are the gravitational field and the electrostatic field. So let us write it down. The formal definition is: in a region of space, if to each point P a vector, and let us call the vector A, is defined, we say that a vector field A exists in that region of space. And we have given examples. The gravitational field, the electrostatic field, so this is a region where a vector is defined, hence it is a vector field. And in the previous case, this is a region where a scalar is defined. And in the same region, we might have a scalar field as well as a vector field, because in this region, apart from the electrostatic field, the electrostatic potential is also defined. Let us consider another example. Let us consider a tube through which some fluid is flowing. So this is a flow tube, and at any point, say this is the velocity of flow. So V is the velocity of flow, or the flow velocity, and velocity is a vector quantity, so it can be written as V into V cap, and this V is the speed of flow. Now this V is a function of space, because velocity varies from point to point in general. So this region is a vector field, and the corresponding vector is V. And here we have a fluid flow. We will talk about vector differentiation. And we will introduce a new operator which is called gradient operator and is widely used in physics. Let us start with total derivative. Let vector A be a vector function of the coordinates x, y and z. Then what is the definition of ddx of vector A? This is defined as limit delta x tends to 0 of this ratio. Let us write it down more elaborately. In the denominator we have delta x, and in the numerator we will allow all to vary, and that is why the name total. So x goes to x plus delta x, y goes to y plus delta y, z goes to z plus delta z. So this is the definition of total derivative. So the main point is that in total derivative all variables vary. In our case, x, y and z. Hence the name total. And obviously, as x, y and z goes to x plus delta x, y to y plus delta y and z to z plus delta z, vector A shifts to vector A plus delta A. And the ratio of vector delta A by delta x as delta x tends to 0 is defined as the total derivative of vector A with respect to x. So it is variation of vector A per unit variation in x as delta x tends to 0 as all variables vary. There is another type of derivative apart from total derivative which we mention now. We define now what we mean by partial derivative. In total derivative, all variables will vary, but in partial derivative, only one variable will vary, keeping others constant. So let vector A be a function of x, y, z. Then we define partial derivative using this del sign. And we define it as this is the definition of total derivative, and therefore we have to attach to it certain restrictions. And the restriction is that all variables other than x will be held constant. Only x will vary. So we will take y to be constant. We will take z to be constant. So let us write it in details. The denominator will have delta x. Now we have to write it carefully. Vector A is a function of x, y, z, and we allow only x to vary. That is, x will shift to x plus delta x, but y and z are constant. So this is the definition of partial derivative. So here only the relevant variable, here x, varies. Hence it is called partial derivative. So as x goes to x plus delta x, but y remains y, z remains z, vector A changes to a plus delta A. Then the ratio of delta A to delta x as delta x tends to 0 is defined as partial derivative. So partial derivative refers to variation in A per unit variation in x as delta x tends to 0, keeping all other variables fixed. Let us now give example of total and partial derivative. So the total derivative of this function xy will be x dy dx plus y d dx of x, which is 1. So it will be x dy dx plus y. And the partial derivative will be, we are differentiating with respect to x, which means y is constant and therefore y goes outside. And this is 1, so it is simply y. So this is one example. Let us give another example. Now df dx is given to be x, which means the value of df is x dx, and we can integrate and since it is an indefinite integration, a constant c will come, which is called constant of integration. Now this is f and this is x square by 2 plus c. So this is the answer, and c can be found out from boundary conditions. This is constant of integration. Let us check whether things have been done correctly. Starting from this result which we got, let us find df dx. And this is indeed x. So we have got df dx equal to x. So the calculation is correct. We do another problem. It is given that del f del x is x. We have to find the value of f. Now del f del x is x. Please be careful. We cannot write in the next step del f is equal to x del x, because del f has no meaning. Del del x has a meaning. This is called partial derivative. With respect to x. Also, note that dx has a meaning. Dx means a small increment or infinitesimal increment of x, or elemental increase in x. So if this is x, so this is origin, this is x. Now if you go by a further amount which is extremely small compared to this length, then this length can be denoted by dx. So dx is a length along x which is as small as you please, and del x has no meaning, just as del f. So we should be careful that del x or del y or del z or del t, they have no meaning when treated individually. But del t, del x, del y, del z, they have a meaning and they represent partial derivative. So let me say it once again that del f del x equal to x does not mean del f equal to x del x. Now we are to find the value of f and we have to write it directly in the next step. F equal to, now we have to write a dx integration, but at the same time we have to incorporate the fact that here, it being a partial derivative, y is constant, which means we can add any function of y in this expression and the constant of integration c will be there, and we'll check it. So this is equal to so this is the answer, and let us check whether we get back del f del x equal to x starting from this expression. Let us start with this expression. Here we have assumed that the variables involved are x and y. Now del f del x will be partial derivative with respect to x means y is constant and therefore it will give us 0, and what we are left with is 2x by 2, which is x. So indeed we have got back del f del x equal to x starting from this result. So what we did was correct. Let us do another problem. Del f del x is equal to y, then we have to find the value of f. So let us start with del f del x equal to y. Now this does not mean that del f equal to y del x. This has no meaning, and we have to write things directly. So we have to write f equal to y dx, and then we have to place the integration sign, noting that in this problem x only varies and y is constant. Therefore the integration sign will be put in such a way that y is outside the integration sign, and we have to add to it all the constants apart from the constant of integration c. So in this problem, apart from x, the variable involved is y, which is constant. So we have to add g of y, which is constant in this problem, though in general y is a variable. So this is the answer, and we'll check whether we have done things correctly. Let us check whether we have got things right. So we'll start with and let us calculate del f del x. Now this is 0 because we are taking derivative with respect to x, treating other variables to be constant. So gy is a constant so far as this operator is concerned. So this part will give us 0, and here y is constant, it goes outside, and what we get is simply y, and therefore we have got things right. Let us move further. Let vector A be a function of x, y and z. Our task is to find dA. Now we note that vector A shifts to vector A plus dA, and such shifting is due to the changes that x shifts to x plus dx, y shifts to y plus dy, and z shifts to z plus dz. And since A is a function of x, y, z, these changes will have an effect on vector A, and therefore it will also change. Now we have to find or evaluate the value of vector dA. How is it related to these changes? Now consider change in x only. That is, y and z are held constant. Then this will be the rate of change of A with respect to x when other variables are constant. So we can write it as change in vector A per unit change in x. And the problem is virtually solved if we follow the following arguments. Here note the term unit change in x. So if x changes by unity, then this is the change in vector A. So if x changes by say dx, then what will be the change in A? Then change in A is, for unit change, the change in A is del A del x. So for a change of dx in x, A will change by an amount del A del x into dx. And in our calculation, y and z were held fixed. Now let us make changes in y only, keeping x and z constant, and in that situation, if y changes by dy, then change in A is, simply replace x by y, and if z changes by dz, holding x and y to be constant, then change in A is del A del z dz. So note that this is for x only change, this is for y only change, this is for z only change. Now if all changes, that is if x, y, z all changes, then the total change suffered by A will be A goes to A plus dA, and this dA will be the sum of all these three quantities. So we have dA is equal to del del x of vector A into dx del del y of vector A into dy del del z of vector A into dz. And this directly follows, therefore, from the result from the functional dependence of vector A on x, y and z. So what if vector A is a function of x, y, z and t? So similarly we get dA is equal to, we'll have an additional term for t, and what will be the total derivative then with respect to t? The total derivative is dA dt divide by dt throughout and dt by dt is 1. A few words about functional dependence. Which is of two types. One is called explicit dependence and the other one is called implicit dependence. We'll describe it through examples. Let us consider a function f is expressed as f equal to x square. X is, say, sine of t. It follows that f is a function of x. F is a direct function of x. And here too, x depends upon t directly. And let us investigate it a bit more carefully. F is a function of x, but x is a function of t. So f depends upon x directly, but depends upon t indirectly through x. So there are two types of dependence. So let us write them. F depends upon x, and here too x depends upon t. And this dependence is called explicit dependence or direct dependence. Which we can see through our eyes. But there is another type of dependence, that f depends upon t through x, and this is called implicit dependence or indirect dependence. Let us give another example. Suppose f is x square cos t, where x is sin t. So in this problem, f is a function of x and t, and x is a function of t, and these dependencies are direct dependence. But we note that f depends upon x and x depends upon t. So f depends upon t in two ways. One is implicit dependence, the other one is direct dependence. So f depends upon x, f also depends upon t, and x depends upon t. And these dependencies are explicit dependence. And the dependence of f on t is an implicit dependence. We will now take up directional derivative. Let us consider a region of space at each point of which a function psi is defined, and we call it psi field. So we can take the origin, say here, and let this point have coordinate vector r. So psi is a function of x, y, z, or in other words, psi is a function of vector r. And vector r is the position coordinate of a point in this region where at each and every point psi is defined. So consider this psi field. Now this direction is r cap. Now let us ask this question, that how does psi vary as we move along this direction? In other words, we wish to find the rate of change or variation of psi as we move along r hat. And this is obviously the derivative of psi with respect to r. This is by definition, and this is referred to as the directional derivative of psi along r cap. We can write it explicitly also. Let us use this relation. Psi is a function of x, y, and z. Now if x changes to say x plus dx, y changes to say y plus dy, z changes to z plus dz, we are moving in this region. Then psi changes to psi plus d psi, where d psi is given by, as per our derivation, del psi del x into dx, which is the change in psi due to change in x only, keeping others constant. And similarly we have the y term and the z term. And addition means we are considering all changes and what is the effect on psi due to all these changes. So this is what we get. Moving along r cap means r changes. So if we are here at r, then we wish to move by an amount dr along r cap. So r will change to r plus dr. So moving along r cap means r goes to r plus dr. So we have d psi dr. Here we have divided throughout by dr to get the directional derivative of psi along r cap. So this is the expression of directional derivative of psi along r cap. I'll go to the next topic, that is gradient, saying once again that directional derivative refers to the rate of change of psi as one moves along r cap. This is a psi field. At each and every point, psi will have different values. If we are proceeding along a particular direction, say r cap, how does psi change? And that quantity is referred to as directional derivative of psi along r cap, and the mathematical expression is this one. But we will soon get a very short expression for it in terms of gradient.